Hello everyone, welcome to another video of quantum field theory. In today's video, we will be talking about what is called semi-classical gravity. So let's begin. So semi-classical gravity is just quantum field theory on a curved spacetime, where we treat the spacetime as just being classical spacetime. So here is the action for semi-classical gravity. As you guys can see, we are working with a scalar field, and we can see some sort of similarities between the semi-classical gravity action for quantum fields in curved spacetime and the action for quantum fields in flat spacetime. We still have this same mass term, but we pick up another term, this one over here, and we also use the general metric tensor instead of the Minkowski metric. We also see a square root of negative g over here. Now, what do all of these parts mean, and where do they come from? Well, g is defined as being the determinant of the metric tensor. And we include this term over here in order to make our volume element invariant under general diffeomorphisms, which is like the Lorentz transform, but for general relativity. It transforms between different frames on that curved spacetime. You can also think of a diffeomorphism as a morphism in the category of smooth manifolds. So we also see this R term over here. This R is what is called the Ricci scalar. The Ricci scalar tracks how objects change their volume along geodesics. So the Ricci scalar, the big important thing is that it's zero for a flat spacetime, and it's non-zero for a curved spacetime. And this term is going to couple our actual field to the Ricci scalar. And by putting this action into the order of Lagrange equations, we will obtain this equation right over here. So how can we go from this equation in some general spacetime to the Klein-Gordon equation in flat spacetime? Well, first of all, we can note that for flat spacetime, g mu, or partial mu of g mu nu equals 0. This is also true for some curved spacetimes as well. But for flat spacetime, our metric tensor does not change depending on time nor space. So that means that we can just move this to the front, and these will cancel out to give us 1. And we can also move this to the front as well. That will just give us g mu nu partial nu plus m squared plus epsilon r times our field equals 0. Now, we can look at this term right over here that's coupling the Ricci scalar to our quantum field. This actually breaks the equivalence principle, since remember that the equivalence principle states that a falling object cannot locally distinguish itself from falling and floating in empty space. This term in our Klein-Gordon equation says that it actually can, because for an apple falling down, the Ricci scalar is non-zero. But for an apple floating in empty space, flat space, the Ricci scalar is actually 0. This implies that an apple that's falling down will see quantum effects that are different from an apple that is just flying in empty space, due to the fact that the Ricci scalar does change between those two scenarios. Even locally, the Ricci scalar does not change locally. It's the same locally and globally. So that's going to violate the equivalence principle. So usually, in models of semi-classical gravity, we choose epsilon to be 0. So this term also goes to 0. However, we can also consider models where the equivalence principle actually breaks on quantum scales and further evaluates their implications. But for now, we are going to keep it simple and still have our equivalence principle being satisfied. Also, a cool thing to note here is that this term over here looks like a mass term, where the mass, the effective mass, is epsilon times r. So if we had the mass of like the scalar field to be 0, we would still have something that does look kind of like a mass term in our action. Cool thing to note here. So again, if we choose epsilon to be 0, and r is 0 anyways for a flat spacetime, we will then just have, and this is our Klein-Gordon equation. for when G mu nu is just going to be the Minkowski metric. So we can see how the Klein-Gordon equation is a special case scenario for the Klein-Gordon equation on a general spacetime. So going back to our Klein-Gordon equation on a curved spacetime, the G mu nu, the metric tensor, we could actually quantize it and make it become an operator, just like the free scalar field, where it's going to act on the vacuum state and give us a particle state. Or we can just keep the G mu nu being completely classical, and then just keep the field as being like a normal quantum field. And the approach where we take a quantum field and keep G mu nu be the normal metric tensor, that's called semiclassical gravity. And this over here is called quantum gravity. And there are multiple ways to actually do quantum gravity. There's loop quantum gravity, there's string theory. I hope to make a series on string theory in the future. But there are a lot of these cool different aspects of quantum gravity. But the more chill way, the more safer approach is to just look at how far we can go by just considering the background space-time to be classical. And that's semi-classical gravity. In semi-classical gravity, we can derive a bunch of cool effects like the Hawking effect, which we'll be doing in a future video. So now we can actually look at what's called conformally flat spacetimes. A conformally flat spacetime is defined as a spacetime where the metric tensor, G mu nu, is just a multiple of the Minkowski metric. This is very useful for us since it allows us to write the metric in terms of another metric that we are already familiar with. Also, the Klein-Gordon equation for a conformally flat spacetime can just be written as the same Klein-Gordon equation in the flat spacetime, but scaled by some factor that depends on our spacetime. If we have a conformally flat Klein-Gordon equation, we can again just decompose the field into plane waves and scaled by these coefficients. And again, the coefficients will create and destroy particles in our spacetime. So an important concept that we have to talk about is what is called positive and negative frequency modes. The e to the minus ik mu x mu is called a positive frequency mode because when we actually take the derivative of that, we're going to get minus I omega scaled by the same thing. You guys might be wondering, why are we calling it positive frequency mode if we have a negative sign here? The answer is that for the Hamiltonian, we would have a factor of I here. And that will cancel out with this, which cancels out with this, when you multiply it by I. And that will make omega, that would make our energy equal omega, so our energy is positive. If we had a negative frequency mode, that would just be e to the positive ik mu x mu. And for the same arguments as before, when we multiply that by I, we're going to have minus omega for our energy. Now, of course, we already learned in quantum field theory that all particles have a positive energy. So we get this whole concept of positive and negative frequencies by sort of naively applying the Hamiltonian. But just for historical reasons, we are still going to call them the positive and negative frequency modes respectively. We also talked about this concept before. We just said energy instead of frequency, but now we just say frequency for some reason. So going with that concept, we can note that we have an annihilation operator in front of our positive frequency mode. We have a creation operator in front of the negative one. Now we define the vacuum state as a state where A of k acts on the vacuum and gives us 0. And again, the positive frequency modes are important because they help us define the vacuum due to this relation right over here. But what happens when we work with a different frame of reference on the same curved spacetime? So say we have this red guy over here. Let's call him A. And A uses the coordinates tx. Now B will use the coordinates t prime x prime. Now, B will actually compare A's modes. So this is the mode for A. Now, A said that this was a positive frequency mode, and A was using partial t, where t was the t in A's coordinates. However, B is going to use his coordinate time t prime. And when he applies his time derivative in his frame to the plane wave, he actually might find out that it's not a positive frequency. He may actually get something that's a negative frequency, like plus I omega, after applying partial t prime. He might even get a mix of positive and negative frequencies. So due to the fact that we can't define a global killing vector field, that's the fancy way of saying it, on a curved spacetime, it means that different observers are going to disagree on which mode is a positive frequency in general. And this means that B will say that AFK won't destroy one particle anymore, since AFK was attached to the positive frequencies, but B doesn't say that this is positive anymore. So he might actually see AFK as destroying particles instead of creating them. We can make this concept more concrete by again expanding our field phi in terms of plane waves. So this is what A is going to see. Now B is going to agree on the same quantum field, but B will decompose it in a different way. And B is going to use his own creation and destruction operators, and he will also see his own positive and negative frequency modes that are defined by his own time coordinate. The basic idea here is that since B is going to use difference creation and destruction operators, B is going to count a different number of particles in the vacuum. So for example, since A conjugate K acts on some state, let's call it this, and it's going to give us one particle with a K, B is going to have B conjugate K be his creation operator. And when it acts on the same vacuum state, it might give him, say, 3 particles of let's say K. They're going to disagree on the number of particles in this state. And an important thing to mention here is that the state is the same. They don't see the state as being different, right? We still have the same state that we're looking at. However, it's the interpretation of the number of particles in the state that starts to differ. So since our field can be decomposed into a different set of modes, that means that the modes themselves can be composed of each other, since we have a complete basis. So this means that we can write out the modes in B's frame in terms of the modes for A, scaled by some coefficients. And we call these coefficients the Bogoliubov coefficients. And now this is actually a linear combination, but the sum in this case is going to be an integral since K is continuous. So since we're integrating over K, that leaves us with P, which will be the momenta for B's frame. And by using some logic that we will develop in the next video, we can actually derive relations for B and B conjugate with A K and A conjugate K. So we can also write out the creation and annihilation operators for B in terms of A, and also vice versa, but it's going to be more convenient for us to write B in terms of A. Now these transformations that you see right over here, these are called the Bogoliubov transformations. And we are going to use the Bogoliubov transformation to actually calculate the number of particles that B is going to measure. So how do we actually do that? Well, note that the vacuum state is defined, A's vacuum state is defined as being the state where A of k will act on the state and give us 0. And the number of particles in the vacuum state is also going to be 0. This implies that the expectation value for the number of particles in the vacuum is going to be 0. Because since the number of particles in the vacuum is always 0, the average number is also going to be 0. So we want to see how many particles that B will measure in A's vacuum state. So you want to see B's number operator acting on A's vacuum state. So here we had A's number operator. And to see B's average number of particles in what A calls a vacuum, we would just sandwich the vacuum states with NB. And this will tell us the number, or the average number of particles that B will actually see. So how do we actually do that? Well, it's actually pretty straightforward. We want to write out the number operator in terms of A's number operator, because we are comparing two different things with different bases. So you have to write them in the same basis. So the number operator, if we can recall, is just the integral over p over 2 pi of b conjugate b times bp. Now we already have a relation that relates b conjugate and b with the old creation and annihilation operators. So we can just plug those values in for bp. So here we've written the number operator for b in terms of the creation and the annihilation operators. Also, we wrote k prime here since we're multiplying two integrals together and they're both over k. So we have to actually use k prime for the first one for convenience. And we're going to better understand why later. Also, I'm going to just change these coefficients into, let's change this to dk prime. Because alpha sort of looks like a, and I don't want you guys to mix the a's and the alphas together. So these are going to be d's instead of a's. So we now have this for the number operator. And what we need to do now is sandwich it between the vacuum states to get the average number of particles in the vacuum from B's frame of reference. Now we can note a couple of interesting properties. Note that AK acting on the vacuum state gives us 0 by definition. And since that equals 0, that means that A, the covector for A, acting on A conjugate K, also gives us 0. So when we distribute this state on the inside, this is going to be 0 because we have an AK acting on the vacuum state. And when we distribute this over here, this is going to be 0 due to this over here. So that's going to leave us with having the integral over dp over 2 pi, the integral over dk prime. Note that we used a k prime here. The reason is that we're multiplying two integrals that are both over k. So to make the continuous sum kind of work out, we're going to use the k prime. Or we're going to set k equal to k prime later. So we have k prime and the integral over k. And we had 0a acting on b conjugate k prime p a k prime, and then b, this over here should be just the normal beta. We shouldn't have a conjugated there. So doing that, this would just be a k or beta kb kp and then a conjugate k acting on the vacuum state. That's what we get after setting all these terms over here to be 0. So what we can do now is we can move the coefficients outside of the product since they're just a scalar. So this would just go here, and we can note that this is going to give us one particle with mods of k prime. This gives us one particle with mods of k. So we now have the integral over dp over 2 pi, integral over dk prime, integral over dk, 1k prime interproducted with 1k, times bk b bk conjugate b conjugate, or sorry, bk prime b. And we can note that this is just going to be 2 pi delta of k minus k prime, since we were working with 1 plus 1d spacetime. And then this cancels out with this one over here. And that will mean that k is going to equal to k prime. So that gives us the integral over dp. Integral, I should really have ordered this like this. Doesn't really matter though. But I should really have ordered it like that. And then we'd have dk of bkp p conjugate kp. That's how we have like k equals k prime due to the delta function. And that's just going to be dp dk of beta squared. And that's going to be our answer for the average number of particles. And yeah, that's pretty much it. So while A, remember that A actually sees the number of particles in its vacuum to be 0. However, B's reference frame is going to see this integral over here to be the number of particles. Now, if we were to transform between A and B such that beta is 0, I should really write this as beta of Kp, we can't forget that's the Kp over here. If we were to transform them in such a way where beta is 0, then B would agree on the nature of the vacuum. And this happens when we have a Lorentz transformation. Two inertial observers that are related with a Lorentz transformation will actually see the number of particles in the vacuum to still be 0. However, if the space-time is curved, two inertial observers will actually see them. In general, they will see a different number of particles. Now, it turns out that even in flat space-time, it's still possible to have two observers disagree on the number of particles. And this is the nature of what's called the Unruh effect. In the Unruh effect, the number of particles that an accelerating observer sees will actually be non-zero for the same exact reason. And we will be calculating the explicit value for beta for the Unruh effect in a future video. But that's pretty much how semi-classical gravity kind of works in general. In semi-classical gravity, we see a lot of the time that curved space-time makes different observers disagree on the number of particles in the vacuum. And with that being said, that's pretty much it for today's video. Thanks for watching and have a great day. Bye.